I'd like to welcome Dr. Jesse Feyen. Jesse is the new Deputy Director for the NOAA Great Lakes Environmental Research Lab. He started here in mid-June. And today his title for his presentation is Delivering Impactful Coastal Science Services to Strengthen Communities. Jesse?
Thank you, Margaret. And thank you all for being here. Good morning. I hope everyone's doing well today. I'm excited for the opportunity to speak as part of the seminar series, although having arrived back in the Great Lakes 4 months ago after roughly 12 years at NOAA headquarters in Silver Spring, Maryland, my depth of Great Lakes research is rather shallow. There's not much I could accomplished in 4 months. So I wanted to highlight, based upon my experience in my previous roles, lessons learned that I think are applicable and why I'm excited to be here in the Great Lakes. Just a brief bit of background. Let's see, I will go in chronological order. I was born and raised in Michigan in the Grand Rapids area and went to Calvin College in Grand Rapids to get my undergraduate degree in civil engineering. And then for my graduate work, I went to Notre Dame, which is obviously still in very close to the Great Lakes. And did work on coastal hydrodynamic modeling using the ADCIRC model, focused on developing large-scale models to predict hurricane storm surge simulations for the state of Louisiana. And in 2004, transitioned to NOAA, National Ocean Service, and started to be involved in some coastal inundation modeling work due to sea level rise. But as you'll recall, we had a very impactful storm in 2005 called Katrina. So a lot of the research that I contributed to and was involved in was greatly enhanced and directly involved in the response to that disaster. And that led to a lot of work while I was at NOAA in the coastal inundation arena and dealing with storm surge from tropical cyclones, but also from extratropical storms. And so that's a lot of my, I did a lot of work coordinating that within NOAA. I took a position as the what is called the project portfolio manager for NOAA's storm surge roadmap. So I'm going to highlight that. That's part of my talk today. And then became deputy chief of the Coast Survey Development Laboratory in Silver Spring before recently arriving here. So one of the things that for me, why NOAA has been a great fit for my career is that I'm passionate about not just great science, but the application of that science to improve our communities and our nation. And that's really what's been a motivating factor for me in my career, and something I'm excited that I've observed here in the Great Lakes already. So the NOAA mission, which I identify with, is focused on delivering science knowledge to decision makers. That's my own brief summary of that. But in my experience, that requires multiple factors in order to be a successful effort. It requires knowledge of the users of that science information, an overarching vision to coordinate efforts, partnerships, effective program and project management, and transition of science to application. So really, the theme of this story here is that it requires collaboration in a lot of different ways in order to be effective in having an impact. So I'm going to use some of my experience dealing with coastal flooding and storm surge projects to illustrate these principles and highlight how I envision and have observed these same principles being applied here for Great Lakes challenges. One phrase that Dr. Sullivan has highlighted is the concept of environmental intelligence, and that's really delivering this science information. And it's critical for coastal communities. as you likely are aware, storm surge flooding is a well-known hazard. It's among the largest disaster causing effects in the United States, and I've highlighted some recent significant events that illustrate that, including one that we just had this year, Matthew. Reducing the impacts of these events requires several things. It requires a clear understanding of the science of the problem and an effective communication of what that risk is to the public, to decision makers. And we have many similar coastal hazards here in the Great Lakes, or coastal issues in the Great Lakes, as I'm sure this audience is very familiar with. So first off, I'd like to talk about knowing our users and what their needs are and how we addressed this challenge dealing with coastal inundation. We had a lot of conversations amongst a lot of experts, and sometimes as experts we tend to overcomplicate the problem, but when you look at your users, they often are asking very simple questions. And we captured that for coastal inundation as follows here on the screen. They're asking things like, who's going to get flooded? How much flooding will there be? When will it arrive and leave? What will the impacts of that be? How often it might occur, and what should they do about it? I think as experts we don't often talk in that language. We might talk in much more technical jargon about how we've configured a numerical simulation, and that's not quite the same information that they're looking for. But once we had a clear picture of the questions they were asking, we used that to drive our science goals. So we knew we needed to accurately both predict and assess the water levels that occurred in a storm, and we didn't have the full capacity to do that. We weren't accounting for the full combination of storm surges with tidal signals, with wave contributions, and with river inflows. And also we weren't adequately dealing with uncertainty when we're talking about a forecast scenario. We needed to intuitively describe inundation. So again, move away from technical jargon, from language that was maybe too geographically obtuse, and provide more clear statements and graphics and maps. And then we needed to communicate in a way that led to actionable information. So that really involved a focus on social science, which is understanding your user and what they're trying to do, and really putting yourself in their shoes. I think that's a critical step to our application of science. So we had a multi-pronged strategy for addressing these issues, particularly dealing with social science, so that we could understand our users. First off, we needed to assess what the public needed. We conducted interviews, held focus groups, public surveys. We also talked to partners, emergency managers, media, broadcast meteorologists in a variety of fashions, web interviews, focus groups, surveys. We determined what type of decision support was needed for emergency managers who actually make the call as to when an evacuation does occur. Excuse me. And then we moved into a prototyping phase where we developed new prototypes, in our case an inundation graphic and a watch warning for storm surges. And we evaluated over 100 different prototypes of these new products. And one of the lessons learned that you'll see as I move forward through this is that what we thought as physical scientists was a clear message was really not necessarily interpreted as intuitively as we had hoped it might be, and we really needed to put the ball in the court of the user for determining what would be an effective way to communicate. And that led to experimental products and eventually operational implementation as we moved down through the transition pathway. And we supported this by conducting marketing and outreach. So it really, there's a lot of facets in order to having this successful application of science knowledge. So what did we learn from all this social science? A significant portion of the surge vulnerable population didn't understand what storm surge was. They didn't understand their vulnerability. And they knew they needed more information, but they weren't really clear on how they should get it. And so that's where the prototyping came into play. And they wanted things like an inundation graphic. They wanted information earlier, and they wanted uncertainty information, but maybe not in the way we would communicate it. Some of this work was highlighted in a recent BAMS article, which I co-authored, which is linked below. So I started with the users, but part of that work took a lot of collaboration across the agency. And how did that come about? Via an overarching vision to coordinate our efforts. So we developed a vision statement, and that is to deliver accurate, relevant, and timely information, all of that important to what we are trying to accomplish. And we figured out that the biggest challenge wasn't any science challenge, but was clearly communicating the science. And we wanted to see that lead to reductions in losses of life and property and promote community resilience. And this allowed a lot of different technical experts to come together and focus on what the problem was by having a clear vision. And then we had to bring in a lot of different partners together. So we developed what was called NOAA's Storm Surge Roadmap, and this is an ongoing effort. And the roadmap is an intuitive name. It provides direction. And it made sure that everybody was reading from the same map. There was a common way forward for tackling what is a multidisciplinary challenge, which is a common situation in dealing with coastal science. We had to bring together experts in meteorology, oceanography, geography, geodesy, GIS, modelers, observationalists, many of the same skill sets we have working here in the Great Lakes, social scientists, which I've already mentioned. And we engaged not only our internal partners, but a lot of external partners. So a lot of partnerships with different universities. We partnered with cooperative institutes, nonprofit organizations, sea grant organizations, private industry. It could be partners working with us on communication or contract support from engineering or science industry firms. The bottom line, this was the first comprehensive strategy to holistically address this challenge and establish a community-wide response. So we didn't have each member of this partnership working independently on the problem, but that we were focused and collaborating together. And as you can see, if you look at the outcomes, which are outputs, which are on the right side of this screen here, when we want to get to the stage of delivering an accurate storm surge forecast or flood map or product or science application, it requires contributions from a lot of different areas of expertise in the background. And that may not always be clear or need to be known by the person who's using the product. But everybody who's involved in this process needs to coordinate. And we worked to establish that. I wanted to highlight one of the activities, because this was a particularly exciting and interesting project that we were able to leverage NOAA's Cooperative Institutes to accomplish. Kathy Sherman Morris at Mississippi State applied eye tracking techniques to help us evaluate our prototype inundation graphics. Helped us analyze the appearance of graphics, color schemes, looked at what types of words were most effective, and this was all part of our partnerships and our understanding of our users. One important role that I helped contribute to this process is to the program and project management effort, to a lot of the suite of projects ongoing. So what is project and portfolio management briefly? A project is simply, it's a temporary effort to produce a specific output, develop a new model. So it's about defining that scope, managing schedule, costs, managing risks, and tracking performance. So we had in our portfolio, in our program, on the order of 30 to 40 projects going on at the same time, all pushing towards a common goal. And so portfolio management becomes important because you need to understand what's the right project to do when. And that was really the function that I served. And we established a form of governance over our collaborative efforts. We got buy-in from senior executives in the organization by establishing a cross-line office steering committee. We had a project portfolio manager, which was my function. So I led the team and I assembled and monitored the portfolio of projects. We had a charter that laid out what the team was to do and the scope of the effort, the goals we were going to achieve, and we worked together with that team to establish a strategic plan that laid the foundation for our way forward and summarized what our users need and where we fell short and how we were going to fill those gaps. So here's one example of how that came about. We determined that we needed to have a goal for how we were going to improve coastal modeling. We wanted storm surge predictions that were ensembles or probabilistic, that were total water level models, that were high resolution, that were large scale to capture the size of the storms, but also were community-based because we needed to leverage our partners. And where did we need to do this? We needed to provide it to all U.S. coastlines. And this corporate vision enabled us to understand where we were already making progress and where we had one-off efforts that were really only focused on part of this problem that really weren't going to solve the underlying issues. And I wanted to spend some time highlighting in these efforts the transition of specific science projects to applications. So here we get into some more of the nuts and bolts of the work we did in this program. So I've been highlighting the importance of understanding your users and communicating. And to be honest, when I started this collaborative effort, there was a lot of discussion on science and how we might improve model resolution or how we might improve the quality of topographic data in the product or in the model and things of that nature. But we took a step back and realized that that was a conversation between scientists. But the bigger challenge was in getting the message out to the users. And they had consistently demanded a product like the one you see here, an inundation graphic. This product is called the Potential Storm Surge Flooding Map. It's a new operational product that's put out by the National Hurricane Center that is based upon those extensive social science studies and testing that I highlighted earlier. What's important about the development of a product like this is that it required the collaboration from offices across the agency. So not only our social scientists, but we had experts on vertical datums, experts on topography data, modeling experts, all who contributed to a piece of this, and the product wouldn't have been as successful if we had not all been coordinated. Similarly, the Weather Service evaluated and is now testing a watch and warning product for coastal storm surge. You can see a prototype. These are both prototype images here, and they're all currently in use. And my area of expertise, as I mentioned earlier, is in coastal hydrodynamic modeling. So I particularly oversaw some of the efforts for improving storm surge model applications that were used in operations or transitioned there. So one of the analyses that we conducted is that we determined that we had two models already available to us that were community-based models that had extensive development from other federal agencies and from academia that we had ready access to. The SLOSH model and the ADCIRC model. But they have very different characteristics. SLOSH is a legacy model. It's been around. since the 70s. It uses a simplification of the governing equations to run very efficiently, and can run a large number of simulations on today's modern computers in a very quick manner. The ADCIRC model is a much more complex numerical scheme and accounts for more of the advanced physics in the problem in the governing shallow water equations, but it's a much more costly model, so many fewer ensemble members would be available. So because we cared not only for accuracy but also for uncertainty, that is the importance of having an ensemble approach to this, we developed a strategy where we would rely on the strengths of each model at different parts in the problem of dealing with coastal inundation. So when there's a lot of uncertainty in where the storm is going, we want to run a lot of ensemble members and use the SLOSH model, which runs very quickly. If we have a storm that's making landfall and we want to know exactly what's going on, we want to use the more advanced model ADCIRC. And that ADCIRC model represented a new generation of storm surge models in operational use at NOAA, both for tropical and extratropical storm surges. So I'm going to spend some time highlighting how we developed and applied this to illustrate one aspect of the collaborative efforts that we did here to improve storm surge services, and sort of drill down into some of the individual science development efforts. So how did we apply the ADCIRC model? And these are some of the most recent developments. ADCIRC is a finite element model that it allows for the use of a large-scale domain that, in this case, extends across the East Coast. You can see in the model grid on the top right. It allows course resolution offshore and with an increase in resolution and computational cost over coastal and inland regions in this model grid down to 200 meters. The model grid you see developed here is the largest grid with this type of resolution and currently in use that I'm aware of. It extends from Texas to Maine. The reason being is during a dynamic hurricane situation or a large-scale nor'easter, extratropical storm, there's uncertainty on where that storm is going to go, and we need to be able to capture all of those potential conditions and potential impacts across the U.S. coastline. But we do want to provide an ensemble approach, so we have been running these simulations and using an ensemble of forcing, which I'll highlight later here. We take, in this development, we took two different approaches for forcing for tropical cyclones and for extratropical cyclones, which I'll highlight here. All part of the NOAA suite of NOAA operational models. So this mesh, which I just highlighted to you, has roughly 1.8 million nodes and goes down to a resolution on average around 400 to 500 meters, reaching down to as small as 200 meters. You can see the part of the north edge of Manhattan here near the Hudson and Harlem and East Rivers to give you an illustration of scale. We included as many major rivers as possible that we could resolve with this level of resolution in order to promote that total water prediction concept that I highlighted earlier. And we did a lot of work in making sure that we had access to the latest hydrographic survey data and topographic data, both LIDAR and USGS National Elevation Dataset data, in order to populate the model, because having an accurate understanding of the land surface really has a strong impact on this problem, the coastal flood problem. A lot of effort was taken by our partners. We had two subcontractors who really led the development of this effort, Riverside Technologies and AECOM, an engineering firm, who really developed and tested this grid and worked to, along the U.S. Atlantic and Gulf coasts, make sure that the model reflected the narrow channels and features that were along this region. Thankfully, by doing collaboration with partners, we were able to leverage pre-existing grids in many regions and enhance them for our purposes. Here's an example of how the mesh was developed along the Texas coastline. The mesh development software, this is the SMS product, allows you, it's a GIS type interface, allows you to set these arcs in place where there are specific features that you want to represent in your coastal modeling application, and then it will fill in the model mesh according to the parameters you set. So you can see the level of complexity that we were able to capture. So once we had developed that mesh, we needed to demonstrate that it was fit for use through a validation process and how valuable it could be for application. So we did this in a two-step process. The first step was to use the best available wind forcing that we could access, which is a data assimilation-based product. Typically, there were a couple of different sources for that depending on storms that we looked at. And then we would use the wind product that would be available in real time. So the first step helped us isolate the performance of the storm surge model itself. And we ran, this is the list of storms we ran, 10 storms here, and these were all major storm surge generating events and provided as best coverage as we could get across the U.S. coastline. The data set that you would like to have to validate a storm surge model is not very extensive because there haven't been that many well-observed coastal flooding storms. So there have been very significant storms, but this is not an event that happens every year, every month. It happens only occasionally, and not all events have been well observed in terms of scientific observation. Here's an example of the model simulations that we generated with this grid for Katrina from 2005. Looking at the high water marks that were collected by the USGS in this image, you will see the contours reflecting the maximum water level, and these circles here that are above, you can't see, can't point up there, but circles here that are above the contours reflect what the observed water levels are, and the contours represent what the modeled water levels are. And we use that to understand how consistent we were and what the local variability was, and can also produce the type of statistical analyses that you see in the graphic in the lower right-hand corner here, which plots the observed, let's see, simulated water level on the x-axis and the observed water level on the y-axis, and how close they are to. We want them to all lie exactly along that one-to-one line between the two, so sometimes the model in this case might slightly overpredict and sometimes it might underpredict, and we can use this to understand the performance of the model. So we did this type of analysis for all those storms that I highlighted. We could also look at the time series. So for Sandy in this case, these were some of the validation simulations. The blue line here is what the observed water level was. This is at Kings Point, which is in the western Long Island Sound. And the green line is what the model simulated, and the red is the difference between the two. This is in feet above mean sea level. And then in that graphic on the right, those are the peak or the high water mark errors at those specific locations. That is the difference between the peak storm surge, because that's the primary variable, and the observed storm surge for this area. So you can see here the green line tracks the observations, the blue line, very closely at Kings Point. Here we are in the New York Harbor at Bergen Point. And you can see this is a very severe event. Sandy was for the New York Harbor region. That's a lot of water, 12 feet above mean sea level. Atlantic City, flooding continued down the Jersey coastline. This is 7 feet above mean sea level at its peak. And you can see the tidal signal. I know we're in the Great Lakes, but that regular oscillation you see there is a tidal propagation. And this is the model simulation for Cape May, which is at the southern tip of New Jersey. And so we did these types of evaluations throughout the model grid in order to demonstrate its skill before transition to operations. So looking at all the storms we ran, we were able to compile all those statistics. We calculated a root mean square error of 0.85 feet over all the water level observations over that list of storms I highlighted earlier. This is just based upon the storm surge and tidal simulation. Typically the model, you can see this red horizontal line on the left-hand side is the mean root mean square error, and 0 is at the bottom. So the models do tend to have a low bias in terms of the maximum water level predicted, which is typical for this type of application because we haven't incorporated the contribution from wind waves in this simulation. That's an upcoming effort. And then we took that same model and we evaluated it for those same storms using the same forcing that would be used in operational application and evaluated ensemble predictions. So we would take a National Hurricane Center forecast track and perturb that track. So you're probably all familiar with the cone for a hurricane forecast, and down the middle of that cone there's the official forecast track. But there's still uncertainty in where the storm will go. That's what the cone represents. What time it will get there, what the strength might be. So we would vary the variables from the official forecast to create an ensemble approach and use that to potentially provide guidance, for example, to forecasters. So here's an example of how that would work for an ensemble prediction of Hurricane Sandy and the storm surge it caused. So if we looked at the storm surge contours here, this is the maximum water levels, in this case in meters, above NAVD 88. You can see the distribution of the maximum storm surge, where the warm colors are the highest water levels. For the official track for this specific advisory, the advisories are released every 6 hours, typically speaking, for this type of event. And you can see the time at which this advisory was released, so that would have been the forecast at that point in time. If that storm made a landfall earlier, the storm surge distribution would change. If it became more intense than it expected, the maximum water levels would increase. If the track shifted, for example, to the left, the location of the maximum storm surge could increase, or if it shifted to the right, it could significantly change the impact of the storm. And all of these factors relate back to the issues that I highlighted at the beginning of my talk, which is when it's not simply the science understanding that's important to the application of science, but an understanding of what the user is going to interpret and use this information for in their decision-making process. So different decision makers actually had different requirements for information. An emergency manager might very much want different scenarios like this to understand the potential impact. For example, if you were in western Long Island in Nassau County, you would be very concerned what might potentially happen if the storm happened to shift, in this case, further northeast. But if you wanted to send out a broad-based message, a national message for what the hazard would be, you wouldn't want to only portray one potential scenario, but all potential scenarios, and that's where that inundation graphic came into play that I highlighted earlier. So these slides summarize some of the recent developments in tropical storm surge prediction as part of this collaborative vision for improving coastal flood services within NOAA. We also similarly made other improvements, which I can't highlight everything that all the projects that took place within this effort, but there were other applications that were developed in the laboratory where I worked that applied ADCIRC for extratropical surge prediction. You can see a model grid here in the Western Atlantic at the top of the screen, and that model is running operationally at the National Weather Service's National Centers for Environmental Prediction. The one on the bottom is in the Pacific. You can see the west coast in Hawaii is that black blob near the bottom. And currently there's a model in development for the Western Pacific region and U.S. interests out there. And then we partnered with the Weather Service to provide operational products. So this model application runs 4 times a day year-round, predicting tides and water levels for use by coastal flood forecasters. It goes out, each cycle goes out 180 hours using what's called GFS, the Global Forecast System, as wind input to this. And we looked at how we wanted to continue to collaborate towards a total water modeling approach in the future, where we combine the storm surge model here in purple with wave models, which I referenced earlier, with hydrologic models to provide the interactions between the coastal flooding and river flooding. This is something that just occurred in Matthew, and make sure that all of these efforts could be tied together to the operational flood forecast products. And so, for example, we tested, in order to support a future operational transition of this capability, connections between inflows from a hydrologic model, in this case in the Tar River in North Carolina. For Hurricane Floyd, ironically, the flood levels from Floyd were just recently exceeded in this region, but this was previously the sort of historical maximum flood for this area. And we looked at different strategies for connecting hydrologic models with coastal hydrodynamic models by trying to understand where would be an optimal location for information to be passed back and forth within an operational setting, because in operations it isn't necessarily straightforward to dynamically couple and pass information back and forth between the models as frequently as you'd want to, which might be every minute or two or something shorter than that because of the costs of doing so from the operational modeling perspective. So let's see. I just want to conclude with a few slides highlighting how I feel like these principles are important to our application of science to Great Lakes communities. I've been, since I've arrived, and for the work I've observed at particularly Glurl here where I'm located, that there are many great applications ongoing and potential for the future here in the Great Lakes. So we have had the benefit of going through a recent strategic planning cycle and developed a new strategic plan that laid out a vision for us to unify under. We have a lot of trusted partnerships already in place in the Great Lakes area, including our Cooperative Institute partners. Thank you for helping to sponsor this seminar series, and the NOAA Regional Collaboration Team, lots of different types of organizations. One of the most exciting aspects of working in the Great Lakes is the binational aspect of that. And we continue to work to understand and partner with users and stakeholders of the science information that we provide in a lot of different capacities. We are advancing our project and program management efforts, and I've been excited to be involved in these already since I've arrived. Our annual operating planning process, which I won't go into much detail here, and also how we are going to track and manage our performance. And then I think most exciting is the transition of science to applications, and there's been a lot of examples of this that were highlighted in the lab review, so I stole some slides for that, which I'll highlight here in a minute. This graphic, I think, clearly illustrates at Glurl how we are tackling this problem, and this is the adaptive integrated research framework that is laid out in our strategic plan for the 2016 to 2020 period. And like the principles I identified based upon my experience, we have a clear vision statement laid out. We have engagement with stakeholders, which is a key part of applying science. We have partners who are working with us to conduct this research. We will and continue to employ project and program management to assess and evaluate our efforts and our performance and how well we are managing our research efforts. And then we'll focus on that critical step, which is the transition pathway, and that this framework allows us to reach that advancement of science applications and service here in the Great Lakes, which is one of the reasons why I'm excited to be here. And as I mentioned, these are examples of similar applications here at Galore that I'm already familiar with. In particular, Great Lakes Operational Forecast System, which I helped to or was aware of the transition of to the National Ocean Service back when I worked in the National Ocean Service with many of the partners there. There's also examples in hydrologic modeling or the HAB applications, all great, I think, examples of a community-based approach where we're delivering science to users. And with that, I will open the floor up for questions, and thank you for your time. Any questions in the room? So the question is about the model application that we used here. And yes, for the storm surge applications, both for SLOSH and ADCIRC, there are two-dimensional depth integrated model simulations, and there's been analyses. I was part of a project that was coordinated by the IU's office in NOAA to evaluate in a coastal ocean model testbed different strip modeling strategies that demonstrated that in most cases a three-dimensional model is not beneficial or necessary for predicting coastal flooding. It's not a significant part of the dynamics of the problem and increases cost. So that was one factor taken into consideration in terms of how we could be optimally modeling this problem. Just say it again. Oh, yes. Yeah. So the question was, do we have wetting and drying in these model boundaries, and does it allow for coastal flood prediction to occur as the storm increases? In some of the operational applications, it is not implemented because they are it reduces computational cost. But in the model application I spent most of the time on, that tropical storm surge prediction model, it has extensive wetting and drying capabilities. You probably could tell that from the model grid examples that I highlighted over Texas or over coastal regions. So yes, wetting and drying is an important part of the problem. Ellen?
Can you talk a little more about how you communicated the results of modeling to the decision makers, the resource managers, and how they might have used, or how they are using this in their decision making and their management?
Yeah, so the question is, and I'm repeating the question for the online folks, is how are model outputs communicated to users and managers of models? And most of this effort is focused on operational National Weather Service applications, so I'll highlight that primarily. What is an important part of this transition pathway is understanding the constraints and the operational infrastructure already in place. So you all are familiar with receiving a forecast or a watch or warning from the National Weather Service, and there is a computer system and prescribed data formats and bandwidth constraints and everything that are in place for any model guidance that is output from models that needs to meet in order to be used by a forecaster to create an actual forecast. So a lot of this work was focused at that particular infrastructure. And so that requires a lot of communication and coordination and conversation about what data formats, what resolutions you can use, and things like that. The other thing that I highlighted in terms of communicating to managers was specifically that inundation graphic. And so that's where the social science came into play. That product is not done through that operational forecast infrastructure. It's done through an Esri ArcGIS application. And in there, a lot of the work was done by going and visiting with the managers and asking them questions like, what problems are you trying to solve? What information do you need? Giving them examples, asking open-ended questions, and then coming back to them with those prototypes. As I mentioned, we had over 100 prototypes for that graphic to get feedback and scientifically analyze how well our prototypes were understood. So we didn't just give them something and say, do you like this? You know, we had social scientists who would study how well people understood it, and by asking them to use the product. And so that led to all sorts of decisions as to like level of detail, do we include geographic name places, the level of zoom that's allowed, the colors. There was a version that was not suitable for people with color blindness, all these kinds of issues that came into play. So it was analyzed from that perspective. Does that kind of answer your question?
Yeah, so do you have any ability to follow up and assess the impact of the models on the community?
That's an excellent question. So the question was, do we have the ability to follow up and assess the impact of these? There is continuing ongoing efforts from a couple of different perspectives. One is a local forecast office is always engaged with the local community and gathers input from local emergency managers and broadcast media. That is not a scientific assessment, but that is an important way feedback is gathered because they're close partners. There are continuing efforts to do some social science analysis of the effectiveness of this, but not significant. I can't point to a significant individual project that has done an assessment in this case. Brent. Some people can't read maps, to be honest with you. And so if you say flooding is going to reach Ann Arbor, or more specifically, it's going to reach the south side of 94 in Ann Arbor, not all of the users will be able to interpret if that will affect them or not. And so even though, technically speaking, you might be very precise in your language, doesn't mean that the message is going to be received by the user and understood and acted upon in the correct manner. And when dealing with life-threatening hazards like coastal storm surge flooding or inland flooding, or it could be other applications, understanding who the user is, in this case it was general public, we needed to craft the product differently in order to communicate them or provide them with a different product. And that's why there's a watch warning to supplement the inundation graphic, because for many folks it's too technical of a product. So the product has to be targeted to the audience that you're trying to serve. Emergency managers find the inundation graphic more useful because they're used to working in GIS frameworks and obviously have an intimate knowledge of their local region and geography. But that's what I was referring to. That was an example of something that wasn't intuitive to a physical scientist. And our group so we had a group of modelers and we thought we developed a great product, and people were like, this doesn't make any sense to us. So this is a note of caution for all of us who are in that boat. I think that's many of us. Are there online questions? All right, anything else? Well, thanks so much for your time. I was excited to be able to share some of my previous experience, and I hope you all have a good rest of the week. Thank you.